Hello. Well, this week we have Julien Lesgourgues from Aachen University talking about a paper that dealt with whether we can measure the neutrino mass state using cosmology. I found that very interesting because normally we've got a lot of evidence that we will measure some of the neutrino masses, but it'd be cool if we could go beyond that. And Julien and his collaborators talked about that. So can you maybe start and just tell us what you did in the paper?
Yeah. So as you just said, with cosmology, we expect to get a measurement of the total neutrino mass. And the paper wanted to see if we can go beyond. And unfortunately, the conclusion is not. We believe that we will not be able to detect the mass splitting, and thus we will not be able to make the difference between models with a normal hierarchy, inverted hierarchy, or degenerate masses sharing the same mass.
Cool. That is kind of a sobering conclusion. You did, I think in the paper, mention that maybe with 21 centimeter radiation with the best case scenario it might be possible, but probably not with realistic scenarios.
I don't think with realistic settings. We don't know what 21 centimeter surveys will really be able to do in 20 years from now. It depends on lots of unknown foregrounds, but we do include some 21 centimeter surveys in the paper. We do take into account the sensitivity of something like SKA1, and it's not enough really.
So if you wanted the audience to just take two simple things away from this talk, like if that was all they got from it, what would those two simple things be?
I think I could outline a take-home message for a particle physicist and another one for a cosmologist. For the particle physicist, I would say that in a few years, we hope very much that we will get a detection of the total neutrino mass. And if the number we get is still compatible with both normal and inverted hierarchy, then what we say is that cosmology will not go further. So the particle physicists, it's good news for them. They really need data from something like June or Juno to learn what is the hierarchy. So from this point of view, it's good to know, because we tend to say that Catherine, for instance, will not have probably much to measure about neutrino masses if cosmological constraints are correct. Mm-hmm. Okay, and here we say the opposite. We say, no, guys, you really need your big laboratory experiments to get a conclusion. And the take-home message for the cosmologists would be that if in the next year you are trying to infer neutrino masses from data or to make forecast of what can be done even in 10, 20 years from now, you just need to bother with taking three different neutrino masses. You can work with the assumption that the three masses are degenerate and the error you make is negligible compared to any reasonable expected sensitivity.
I see. I guess this is assuming that it's just the standard model neutrino and there's nothing funky going on.
Sure, this is without light sterile neutrinos or things like that. Okay. With light sterile neutrinos motivated by LSND mini boom or something like this, you could get more handle. You could get some hints of at least two different masses if the scenario is true.
Cool.
So really our paper was only on the active neutrino masses.
Yeah. So this question might be a little bit obvious, but like flesh it out a little bit. So why did you do this? Why did you look into this?
Okay. So first, let me insist that this is a paper I did with two people, with Maria Arcidiacono, who is in Milano, and Steen Hannestad, who is in Aarhus in Denmark. It's not the first paper doing such a claim. There have been many papers addressing the same question before. I think the situation was still not really crystal clear, maybe because of a few papers claiming that maybe you can see something. And we were not convinced. We wanted to prove it again with new tools. For the first time, we prove it using Bayesian evidence, which had not been used before in this context. And also there were some analyses saying, probably you cannot detect the mass splitting, but without a true physical discussion of what are in detail the physical effects of different mass splittings on the observable. And our paper has a long discussion like that.
Okay, cool. So what was it that you did in the paper? What's the nitty-gritty?
Yeah, okay, so this is our paper. And when discussing the paper, I will be referring to acronyms for different scenarios for neutrino masses. NH will be normal hierarchy. This is a case when you have one heavier neutrino and two lighter ones. IH will be inverted hierarchy. And this is the opposite case where you have two heavier neutrino and one lighter one. And then I will refer to a few proxies, and in particular to an approximation called DH. It's a degenerate mass scenario where you assume that the total mass is equally shared between three species. And then let me briefly mention two other proxies. You can do some cosmology. You can run your cosmology codes assuming one massive and two massless neutrinos. This is what I called here proxy one. Or you can assume two massive ones with equal mass and one massless. And if you are new in the field, you could think that if you want to mimic a realistic normal hierarchy case, you should use proxy one. If you want to mimic IH, you should use proxy two. It would make naively seem very reasonable, but it has been shown already a long time ago, like 15 years ago, that it's absolutely not true. Surprisingly, the proxy which is always the closest to realistic NH and IH is DH in all cases. The fact that proxy 1 and 2 have completely massless neutrinos means that they are bad approximations. Okay. So even with current data, you can try to see a little bit of difference between, for instance, NH and proxy 1. I see. While DH will remain a very good approximation even in 20 years from now. This is one of the things we will prove here. So in this paper, I will not refer anymore to proxy 1 and 2, but I will only compare NH, IH, and DH.
Okay. And it's called normal hierarchy because like the neutrino that is closest in superposition to the electron neutrino would be the lighter one, and the one that's closest to the muon neutrino would be the next heaviest one. And then yes, the inverted exactly. Has that. Oh, yeah, okay.
In your parameterization of the delta m square between neutrinos, knowing which hierarchy is the correct one boils down in knowing a sign, the sign of a delta m square, which is inaccessible to current experiment. They only measure the absolute value of the delta m squares. Right. Okay, so this is a plot you see in many papers. It shows the total neutrino mass as a function of the lightest neutrino mass. And if you are in the NH scenario, you should be along the red line, and you can go down to a total mass of 0.06 eV. If you are in the IH scenario, you follow the blue line, and the minimal mass is of the order of 0.1 something electron volts. In gray, we have the exclusion regions from recent cosmological data. In magenta, we have the likely 2 sigma error that could be expected from a combination of Planck plus Euclid. What is important here is the width, of course. It's not the central value. The central value was put on the plot arbitrarily. Mm-hmm. And so if this, in the future, the measurement is centered around 0.06, then that should be a lot of information. We should be able, in this case, basing ourselves only on the total mass, we should be able to exclude inverted hierarchy with a reasonable significance of maybe 3-4 sigmas.
And the reason why this line comes down to 0.06, that's because the delta m squared is essentially 0.06 squared, right? Of the biggest.
That's right. So this is what you get when you really squeeze the masses to their minimum value. Essentially, you send the lightest neutrino mass to 0, and then by playing with the other two delta m square, you get the mass of the light and heavy states.
Yeah. And the inverted one
the total
has...
mass is then close, as you said, to the square root of delta m square atmospheric.
Right. And then the inverted one is essentially twice that, because you've got the two.
It's about twice, not exactly, but it's about twice.
Okay, cool.
Right. So the situation which is really relevant to our paper is if the future Planck plus Euclid measurement is not centered on 0.06, but somewhere higher, such that both the inverted and normal hierarchy cases could be the explanation. So, for instance, if the central value is 0.1 electron volts, which is already not so much favored by current data, but not strongly excluded, then we could be here in the inverted hierarchy scenario, or here in the normal hierarchy one.
Right.
And the question is, can we discriminate using cosmology?
Mm-hmm.
So to answer this, first we really focused on the difference between the physical effects of inverted, normal, and degenerate hierarchies at the level of cosmological quantities and observables. And one plot will be particularly important to understand the rest. This is a plot showing the total background density evolution in either IH or NH divided by what you would get with the degenerate hierarchy. So we have two test cases. In all these plots, there is the black curve and the red curves. So the red curve assumes that you have normal hierarchy with a total neutrino mass of 0.06 electron volts. And you always compare it to its equivalent degenerate hierarchy model, in which you have three masses of 0.2 eV, such that the total is the same, 0.06.
Right.
And in the black curves, you compare inverted hierarchy with a total mass of 0.1 eV with its own equivalent DH model, which would have three masses of 0.0333, etc. Mm-hmm. So again, with the same total mass. So these curves here show the evolution of the total density in the universe and of our neutrino, cold dark matter, everything, as a function of the scale factor, in red for normal hierarchy compared to DH, and in black for inverted hierarchy compared to DH. And what you see that they are the same initially and they are the same at the end, because initially either all neutrinos are relativistic or all neutrinos are non-relativistic. So you can get a difference only in the middle, when in some scenarios, some neutrinos are already becoming non-relativistic, and in some others, they are not. Mm-hmm. And in this transition period, which is redshift from about 1,000 to a few, then you always have more density in IH and NH than in the equivalent degenerate model. Okay. So this is important. It will play a big role in the next slides. And then if you want to be super precise, but I will probably not go to this level of sophistication, if you want to compare the effect of IH with the effect of NH, then you should look at the small differences here, and then it becomes very subtle. For instance, here you see that initially IH is higher, then there is then the curve cross, and they cross again. But most of the time, if you have the inverted hierarchy, you enhance the density a little bit more, just a little bit.
And is that because the neutrinos more like cold dark matter, so redshifts less?
Yes, this is because the IH or the NH include one or two neutrinos which are a bit heavier than when you split them equally.
Yeah.
And so at an earlier time, you already get one non-relativistic species, and this non-relativistic species enhances the total.
I guess this
so
is
it's a
probably
maximum mass
typo where you've got DH 3 times 0.3. It should be 0.03.
That's right. There is a typo here. It should be 0.03.
Yeah. So in the degenerate hierarchy one, the most massive one is obviously lighter than the most massive one in NH or IH.
Exactly.
Yeah. Okay.
Exactly. And that makes the effect. And this has an important consequence. If you look now at the evolution of delta cold dark matter, so the relative density perturbation of cold dark matter as a function of the scale factor. And again, this curve shows the case of IH or NH compared to their respective degenerate hierarchy model.
Mm-hmm.
And you see that initially the curves are 1. So initially, of course, the model doesn't know the mass of the neutrinos, they are not yet relevant. But at late time, there is a suppression of the growth of the dark matter fluctuation. And to understand it, you should look at the equation of evolution of delta CDM in cosmological perturbation theory. So you have a Poisson term, you have a Hubble friction term, and you have some dilation terms. Mm-hmm. The Hubble friction term comes from the fact that if you have more expansion, you slow down gravitational collapse. So it took us some time to understand, and this was new in our paper, to understand what drives the effect. And interestingly, what drives the effect is the Hubble friction term. And it's completely connected to the previous slides. In the IH and NH scenario, you enhanced the total density of the universe during a transition time, during an intermediate period. And then you enhance the Hubble friction, and it is really the leading term that leads to this reduction. So in fact, it means that in the realistic scenario, the growth of cold dark matter is a little bit slower than in the equivalent degenerate scenario. So of course, you expect to see this at the level of the matter power spectrum. And this is another plot extracted from the paper. Now we look at the power spectrum of these different models as a function of K. So it's the power spectrum that in principle we could observe today. So these are residuals in the power spectrum. And you have not only 2 colors, but 2 styles. You have solid lines and dashed lines. So solid lines are when you consider the total matter power spectrum, which plays a role in, for instance, weak lensing cosmic shear experiments. Mm-hmm. The dashed line is a power spectrum of only the baryon and cold dark matter components, which is the one which plays a role in galaxy clustering. Right. So the fact that they are equal to 1 on the left means for very large wavelengths, very small k, all the models are equivalent. And on the right, you see a difference. The difference is very small, it's 0.3%. And of course, we expected it to be very small because what is more important is the effect of the total mass. Now that the total mass is the same in each case, what is left on total of the usual neutrino free streaming effect, which is a big effect, what is left is just the effect of the mass splitting, and it's only 0.3%, it's tiny.
And the free streaming effect is that the neutrinos are very high velocity, even if they're quite massive, even if they're 0.05 eV, and therefore they don't fall into these wells on the larger scale.
Exactly.
But I guess you get a slightly higher power spectrum here because they're slightly more massive in the IH, NH than they are in the DH. Is that right?
Yes.
Okay.
So yeah, so if I would do the same plot for massive models versus massless models, I would get a much, much bigger suppression of the order of 5%. But because I'm only comparing models with the same total mass, I have this suppression. And as you just said, this is related to what we have seen in the last 2 slides. On small scales, the realistic model means more density, more Hubble friction, and there is this little bit of additional suppression. And it accounts for this 0.3%. And there is this funny bump. We explain in the paper why there is a bump. I think it had never been explained before. This is not an effect of Hubble friction anymore. It's an effect of the different scenarios having different individual free streaming scales. For each neutrino with a given mass, you can compute a free streaming scale, which is, of course, the scale on which the neutrino can propagate at a given time. And the effect of the suppression of dark matter growth is related to this and is only effective inside the free streaming scale. So in these different scenarios, you have different individual free streaming scales. This produces a shift of where the effect is important. And a funny consequence of the shift is this bump in the ratio of power spectra. Okay. So the bump goes to about 0.2, 0.3%. So it's already a very, very small effect. So this is the theory. And once you have the theory, you want to see, okay, at the level of real observables, is the effect bigger or smaller than the data from future surveys? Yeah. So if you want, we can go to this section of the paper. Yep. And this is probably most interesting plot. It's now it's reformulated in terms not of the theoretical matter power spectrum, but of the real observable power spectrum that Euclid would measure, including all these effects of nonlinear corrections, bias, redshift space distortions, resolution effects, etc. So it's a matter power spectrum convolved and multiplied by various things. And that's why we get...
do you measure this by n-body simulations with neutrinos that then have all of the Euclid stuff?
It's still done with a linear Boltzmann code, taking into account several corrections from HM code for the nonlinear corrections, and analytic formulas for the redshift space distortion, the Alcock-Pashinsky effect. All this is done analytically or semi-analytically with a class code and starting from linear observables. Yeah. Right. So in principle, n-body simulation would give us the same because HM code has been calibrated on H-body simulation. For instance, you see here a little dip in these curves. This dip is produced by HM code and it fits a similar dip that you get in n-body simulations. Okay. Okay, so our curves are a bit different from the previous plots. You always have the same color code, red and black for IH or NH. Solid or dotted now means different redshift bins. Okay. So the solid is a redshift bin close to us. The dotted is a redshift bin far from us. The yellow curves are harder to see and they are different. It's a direct comparison between one IH and one NH model sharing the same mass. Okay. I don't think we need to go into these details. We can look again at our black and red curve. We see that now, including nonlinear effects, it's not anymore 0.3%, but 0.4%. There is a 0.4% reduction induced by the realistic neutrino schemes. And what looks promising at first sight is that if I plot the observational error from something like Euclid, my residual seems to be bigger than the observational error. Right. Yep. So I could think that, okay, I'm going to be able to detect it. Yeah, yeah. And maybe I'm a few papers in the past said, did this approximation. But the story is not over because first, we don't have only to take into account observational error. We have to take into account theoretical errors, the difficulty to predict observables on nonlinear scales. So this can be
essentially the error on the solid and dashed lines, I guess.
Sorry?
I guess the error on those solid and dashed lines is what you mean by the theoretical error, right?
So the theoretical error now is the fact that usually, the easiest thing you do when you do a forecast for Euclid is to say, be above a given Kmax, nonlinear effect becomes too messy, too dominant. I cannot model them precisely, so I throw out the information. Okay. And usually you do this around 0.1, 0.15, which is this case here. Okay. And then if you only keep data in this region, you don't have a lot of information outside of the observational error. All this is lost. Or you can say, okay, I'm going to model on all scales what is the error I make in my theoretical predictions for nonlinear corrections, for instance. And then you would get another bond that would explode at large K, unlike the observational one. And you would see that it explodes so fast that most of these residuals would be masked by the theoretical error. But we're going to check it in a forecast later on in the paper anyway. And the other thing is that, of course, here we show the effect of only one ingredient, which is changing the neutrino mass splitting. But this effect is likely to be degenerate with lots of other things, with a total amplitude of the spectrum or things like that. Okay, so from this plot, we see that there is a case for looking into more details, but we cannot really draw a conclusion. The next plot is much more definitive. It's the same for the weak lensing observable or for something like Euclid. We see that there is an effect again. There is a residual because 0 is here. But the typical error bar you would get from Euclid, shown here in 2 redshift bins, is way too large. So this is way too small for being detected by weak lensing. And then your third hope could be to get a detection with future CMB experiments, Lightbird, Simon Observatory, Stage 4, something like this. So there is a summary here. It's again some residuals, always with black and red for inverted hierarchy and normal hierarchy. You have a bunch of solid curves which have these small oscillations, which are the residuals for CLTT. Then you have larger oscillations, dashed. These are the residuals for CLEE, the polarization spectrum. And finally, you have something below, it's a residual for CLBB. So what do we see? We see oscillations, and we see here an offset for BB. These are easy to understand. It's another effect that we didn't have before. It's the fact that when you change your neutrino mass splitting, since you change the total density evolution, you change a little bit the angular diameter distance to the last scattering surface. And so you shift a little bit, but by a tiny amount, you shift a little bit the peaks. And if you shift peaks, you get oscillations, of course. So it explains the features we get for temperature and polarization. For the BB modes, it's also very simple. We are talking here about the lens spectra. So here, our BB spectrum comes from the leakage of E modes into B modes induced by lensing. And if we have this realistic scenario, the matter power spectrum is a little bit suppressed. So there is a little bit of CMB lensing. There's a little bit less leakage from E modes to B modes. And thus the B spectra are below. But this is absolutely tiny because the offset of the CLBB is about, again, 0.3%. And the amplitude of this oscillation is about 0.1%. This is negligible compared to the sensitivity even of Lightbird or Pico or Core or whatever.
And obviously very degenerate with any other thing that shifts the peaks by a tiny amount. It
would probably be degenerate with other things like varying delta NF, for instance, the effective neutrino number. But we don't even need to study it because it's just too small. So anyway, we took all the information into account in some forecasts. And we did 2 types of forecasts. Let me explain. In the first forecast, which are shown on the left plot, we generate mock data using realistic normal hierarchy. And we fit it with a degenerate hierarchy model with the mass as a free parameter. So we are supposed to do a mistake because we fit the right model with the wrong model.
I see, yep.
But according to what we said before, the difference between the two should be so small that it should not matter. And we can check this in various ways. We can check it because the posterior that we get is not shifted. It is
Yeah.
still centered on the correct value of the neutrino mass that we have put as a fiducial value. And we can check it also by looking at the evidence ratio between a fit done using the correct model or using the approximate degenerate hierarchy model. So these are the numbers that were the most interesting for us. So sticking to the case of the left, normal hierarchy versus inverted hierarchy.
Okay.
We did 3 fits using the correct model, 3 fits using the approximate model. Why 3 fits? Because we assumed 3 different future data and sensitivities. They are called here realistic, optimistic, and extreme. Essentially, realistic is something we could get in 10 to 15 years. Optimistic, I don't know if we will ever get it, and extreme is almost crazy.
Right.
It's cosmic variance limited, etc.
Mm-hmm.
In all 3 cases, the Bayesian evidence ratio is smaller than 1, meaning that really, if we would have this data and we would fit it with normal hierarchy or with degenerate hierarchy, and we would say, is one of the model a better paradigm to explain the data, we would be completely unable to decide.
Right.
So it's just because the effect I showed before are way too small.
Yeah.
And on the right, we did the same, but now it's for inverted hierarchy. Mm-hmm. So we generate the mock data with an inverted hierarchy scenario, and we fit it either using the correct model or the degenerate model. And again, there is no shift, no bias in the reconstructed value, and the Bayesian evidence ratio are smaller than 1, except in the extreme case where it's 1.5. 1.5 on Jeffrey scale is still peanuts. It doesn't allow you to drive a conclusion. Yeah, so it's a bit sad, but we expected it very much. There have been similar studies in the past by several groups, including also some of us. You can try to probe this in different ways. You can invent a new parameter that will produce a continuous deformation from in a normal hierarchy to degenerate hierarchy, a parameter varying between 0 and 1, and which effect on the mass splitting is to push you from the realistic model to the approximate model. And then you can show that this parameter, which would be defined in a range from 0 to 1, cannot be constrained with future data.
I see.
And so it's true that some papers give the impression that maybe you can do it. But if you look in more details, you see that there are this kind of paper assuming cosmic variance or no noise, or that we can analyze SKA with a full understanding and control on the average thermal history. So non-realistic assumptions, really.
So with this galaxy power spectrum, that seemed like the one that was most promising. And I guess the reason it wasn't promising, as you said, there's theoretical errors. That also seems like the thing that maybe in principle, clever enough future cosmologists might be able to reduce those theoretical errors with better, I don't know, nonlinear simulations of baryons.
You can reduce the theoretical error, meaning if you trust your calculation of, I think not even. Suppose you can trust the outcome of your n-body simulation, including massive neutrino, which is even more difficult.
And baryons.
Up to n baryons, that's a big problem, Up to a level of So I think if you make a lot of progress on n-body simulation, maybe you can control the effect of neutrino masses at the level of 0.1%, but not the effect of baryons. The effect of baryons will pop up on the same scales, and I think will always kill you, unfortunately.
I see. Damn. Cool. Is that anything more specifically on the paper you want to talk about, or is that essentially the?
No. So fans of neutrino cosmology find little technical details in the paper on why you have a bump on this scale and etc. But the general conclusion, I think, we have covered in already.
Cool. And so, as far as cosmology is concerned, it's still guaranteed to get the sum of the neutrinos, but in the kind of vanilla standard model regime, that's about all cosmology will
Yes,
be
I
guaranteed.
believe this is the case. The conclusion is very often challenged. There is a lot of skepticism from people saying, oh, you always put yourself in ideal situations, you neglect degeneracy with other parameters and errors and etc. And no, I don't think. I think that the literature now is full of really realistic forecasts with theoretical errors, with pessimistic assumptions. And I do believe that we will measure the neutrino mass, not even by assuming lambda CDM, but even lambda CDM plus a few more free parameters. The effect of neutrino masses, when you take everything together, galaxy surveys, CMB, weak lensing, DAO, the effect of neutrino masses, in my opinion, is sufficiently different from any other combination of other parameters. And I really think we will see it, even if I know that some people put this in question. I think really that Euclid will detect the total neutrino mass at least at a 2 sigma level, but I hope more, I hope 3 sigma.
Cool. So the next question I normally ask is where to next, but I kind of get the vibe from this one is that you might feel like there's been a kind of full stop at the end of the sentence.
For the splitting, there is full stop.
Yeah.
What to do next in this field is work hard to make the most possible precise assumption in order to measure just the total neutrino mass, and then share the information with particle physicists to see how it fits into their picture and figure out by putting everything together what could be the hierarchy.
And I guess that also anything beyond the standard model that might have a delta NF or something like that is still constrainable with cosmology in very interesting ways. And
of course, the sensitivity to delta NF with future observations is very promising. With experiments like CMB stage 4 and Lightbird, you can reconstruct this effective neutrino number with great accuracy. You can make much stronger statements on these models with light sterile neutrinos. So there will be a lot of information to extract from future surveys. And a very funny situation also would be if we do not detect the neutrino mass, because the arguments for the detection are so strong that if we don't detect it, it's by itself a very interesting situation. It's like if LHC folks a few years ago had not detected the Higgs, then everything would be put in question. So it would mean something very strong. Maybe neutrinos are unstable. Maybe they disappeared from the current universe. Maybe they decayed into a scalar field or something like this. It would be extremely interesting.
Yeah, because I guess from local observations, we measure neutrinos from the sun or something, but they've only been traveling for a few minutes. They haven't had time. They haven't had billions of years to potentially decay. That's interesting.
Yes, of course.
Yeah.
Okay. Yeah. No. We still believe that the neutrinos are around us in the universe because we do measure an effective neutrino number of order 3. But if we don't see the effect of the mass, then we could think that these 3 neutrinos have decayed into 3 different massless species.
Right.
And that could be possible, and then NF would still be 3.
Mm-hmm. Yeah. So the last question is, outside of your own research, what do you think are the most interesting things in cosmology at this moment?
Well, like everybody, I'm very intrigued by these Hubble and my tensions. Actually, both of them, I put more thing. I see lots of criticism passing by, invoking systematic effects, but I also see convincing answers saying, no, we have taken this into account, the tension is still there. So I'm very interested by this, and if it's true, what could it be? So maybe it's modified gravity, maybe it's dark energy, but then it will be very difficult to get a full confirmation, because if it's one of these ingredients, It would be a kind of ad hoc explanation of an anomaly that you cannot test independently. So what excites me more is if these tensions could come again from particle physics, particle cosmology, a bit like our neutrino effect. So suppose the dark sector is not just a boring cold dark matter relic and nothing else. Suppose that the dark matter has interesting properties, maybe it's interacting, maybe there is more than one relic, maybe there is also dark radiation, maybe there is a full complex dark sector with new interactions. And I'm very interested in the how you can probe this with cosmology. And one exciting thing would be that it would explain the tensions, because then maybe the tensions are just a hint of the dark sector of particle physics, and we haven't realized yet. So there are models on the market which give reasonable fits, but not perfect one. And I'm working on this, hoping to find maybe, if lucky, the perfect fit that will give a large H0 and a small sigma 8, starting from a reasonable assumption in the dark sector that could eventually even be tested by some particle physics experiments.
And of course, in the non-dark sector, we have all sorts of complexity. We even have, you know, Juliens and Jeans who've managed to form out of that sector. So it is maybe a little naive to just assume that cold dark matter will be describable by one parameter. Do you have any thoughts on this new tension some people are talking about, where between the CMB and say the supernovae in the omega matter, omega lambda space, when you consider allowing curvature? Is that at the same level of significance to you as the H0 and sigma 8 tensions?
No, I don't think there is any evidence in the data for curvature. I think people who claim there is evidence are using Bayesian statistics in a different way than me. I think that if you promote quantities as free parameters in the lambda CDM model, then you find that omega k can be degenerate with these new parameters. But as soon as you restore data from BAO, supernovae, and others, again, your data comes back centered on omega k equal to 0. So for me, there is not really a matter of debate at this level.
Okay, I guess their argument is that if you do just look at the CMB, it doesn't favor curvature of 0. So, but yeah, okay, maybe I'll let them make that argument if they want to.
So you get this kind. So you get this marginal indication that omega k could be large if you turn on this A lensing parameter, this normalization of the lensing effect. If you make it a free parameter while it's 1 in the standard model. And it's not something physical, but you can say, okay, it's not physical, but maybe it mimics some unknown physics or some unknown systematics that I yet have to discover. If you do this, you find that there is a degeneracy between omega k and A lens. But it's really a degeneracy. It's only if you trust, and it's only because of Bayesian volume effect that you could say it's an evidence for omega k between being non-zero.
Okay.
In fact, there is no such evidence because you have a very flat distribution in this case. And then when you add additional data, then the degeneracy disappears and you get again a nice peak centered in omega k close to 0.
Yeah, I definitely agree with the if you add additional data side, and that you do kind of almost have to only look at the data that is favoring the large curvature. And if you look at just that subset, maybe you can make an argument. But if you look at the additional data, it's smaller. Well, anyway, thanks for your talk today. Anyone who's made it this far, don't forget to subscribe, like the video, and mention it to your colleagues. Thank you.
Okay, thank you.